All right, so thank you very much for coming. So my name is Finkel. I'm from Argonne National Laboratory, and I'm going to talk to you for a few minutes about our integration of OpenMP into LLVM and Clang for the IBM Blue Gene Q supercomputer that we have at Argonne. It's packaged into a product that we call BG Clang, and so say a little bit about that. See how this works. Okay, well, we scroll. Good. And all right, so I'm just going to say a little bit about how this fits in and what it involves. So this is our BG Clang distribution, which is how we package LLVM and Clang on the Blue Gene. It consists of not only LLVM and Clang itself, but also a bunch of other pieces. Sanitizers and C++ standard libraries and vector math libraries, all of which are open source. And specifically, of course, it includes an OpenMP runtime library, which is Intel's library that we've ported to the Blue Gene Q, and the OpenMP patch set for Clang. Again, we've ported that to the Blue Gene Q. All right. And so what does this give us? Well, it means that if you run BG Clang with -f OpenMP, just like on GCC, you get OpenMP support. It comes with essentially full support for OpenMP 3.1, with a lot of pieces from OpenMP 4. The nearest and dearest to my heart is the fact that we get OpenMP SIMD support. So in BG Clang, you can say pragma OMP SIMD, and it will vectorize this loop for you. It gives the optimizer and the backends the necessary hints to know that the loop is safe to optimize, safe to vectorize, even if it can't otherwise prove that from dependency analysis. And again, that's coupled with a runtime library, which is a ported version of Intel's runtime library that they have open sourced, and the Clang OMP patches that Intel has developed. The runtime library, however, has not been optimized, but it does work. Okay, so this is my slide on. So you said you ported Intel's runtime library to the to Blue Gene Q. Well, that's a PowerPC system. It's a big endian system, not a little endian system. Like how does that work? Well, it turns out it wasn't that hard. So Intel's runtime library for their own internal use and experimentation and other things already had macros in it for the necessary memory barriers for non-strictly ordered architectures. But in the version they ship, the memory barriers are just defined to nothing. So we were able to just go in and put in some memory barriers for these macros and turn them on for PowerPC, and we were able to get the correct semantics for the most part. There are still some little endian dependencies in the processor affinity code, but that could be disabled. And most of the code just uses POSIX and pthreads, and so it was fairly straightforward to port that. There's a little bit of assembly that we had to replace in the microtest dispatch routines, but again, that wasn't that hard to do based on the way Clang uses the runtime. So all in all, you got something that works. So again, we took these things from Intel. We actually maintain the trunk-based patches. So Intel produces patches for the latest LLVM and Clang release. We maintain the patches upgraded to the current trunk. We do this nightly, just about. So you can always get the sort of current version, and then we take off of that when we pull a release. And we've been heavily involved in assisting Intel with getting their OpenMP patches upstream, so we can have OpenMP support in the upstream LLVM and Clang. People call this a merging process. It's not really a merging process. It's actually a piecewise rewrite of the entire patch set, which is why it takes a long time. But nevertheless, the quality is really high, and we're very happy about the way it's going on. Obviously, everyone would like it to be faster, but the end product is really quite good, and a lot of companies, including IBM and others, are interested in using it. All right. So the moral of the story is, well, does that all work? The answer is yes, it works. For the most part, I actually have not received any correctness bug reports off of this in a very long time. So I've just compiled a simple table here for an example. I took the unofficial C version of the NAS parallel benchmarks with OpenMP, and I compiled them both with BG Clang and also with IBM's compiler for the BlueGene. And I've just given some timings here for the Class B problem sets. As you can see, well, with the exception of this one, where BG Clang is slightly faster than XL, normally it's slower. These benchmarks are only slightly representative of real code because they actually hammer quite a bit on the OpenMP runtime, which has not been tuned for the BlueGene and may never be. But realistically speaking, for a lot of the real science codes that I work with, it works just fine because for most science code, they do a lot of work inside their parallel loops, and the overhead of the runtime is more or less irrelevant. So for those codes, it works quite well, and we're very happy with it. And using LLVM and Clang with the associated patch sets and everything else, we've been able to deliver a toolchain that has full C++11 support and full OpenMP support on an architecture that wouldn't otherwise have that capability. So with that, any questions? Yes?
So I'm surprised I look like portions of the latest open patch sets. Is there anything specific you have to do for ABI support for KBC64?
ABIs? Oh, I should repeat the question. OK, thank you. Question was, he said he's looked at some of the patch sets for OpenMP. He wondered if there's anything we had to do for ABI support for PPC64. For the most part, no. There are a couple of architecture-specific pieces. So, for example, in the front-end patches, there are architecture-specific callbacks for things like in OpenMP4, when you have SIMD and you say your arrays are aligned but don't provide an alignment. That's an architecture-specific default. You needed some special callbacks to say what that is. That's not a big deal. In terms of the library interfaces themselves, the interface functions are programmed in C, and Clang knows how to generate calls to C using the default ABI, which is what the runtime was compiled with anyway. So that's not a problem. Intel's runtime normally uses a hand-coded assembly routine for doing dispatch. It turns out you don't need that. And the reason you don't need that is because Clang only generates microtasks with up to 4 arguments or something like that, because it actually packs everything into structures. The older Intel compilers used to generate these like dynamically sized variable argument arrays, and that's why they need the assembly bit. But it turns out that they're kind of moving away from that anyway. So I was able to replace that assembly dispatch code with just some C code, and it worked just fine. So yeah, I mean that was essentially it in terms of ABI. I mean the largest changes actually were the memory model changes, adding barriers where they were needed. It turns out that the Intel runtime made some assumptions about places where you could spin to do weighting, and some of those had to be backed off a little bit because on the BlueGene, each core can run multiple hardware threads. But if all the hardware threads are spinning, like hard spinning, then they can starve out the other threads, and so they needed some adjustment there. But it was just some little things like that were sort of very generic that we had to deal with.